Okay, hello everyone, I'm Bill, and today the topic of my presentation is sea level anomaly affect the abyssal current. And first, I will introduce what is abyssal current. Abyssal current means a current with this status, this 3. The temperature is below 2 degrees, and is with high density, and the depth of this current is over 300,000 meters. And the abyssal current I'm going to introduce is AABW, Antarctic bottom waters. And what is the importance of AABW now? And as its name, it comes from the Atlantic Ocean here, and it goes northward to the Atlantic Ocean. And what's important is that it's a major component of thermal highland circulation, and which means it may affect the global climate. And next, I'll link the thermal highland circulation and climate and AABW in this picture. This picture shows the path of thermal highland circulation, and we can see it's all over every ocean. And his job is to regulate the Earth's climate by transporting heat and stored heat and carbon in the deep oceans. And this is why, and this in this region, this is the AABW here. So this is what I said. AABW is a major component of thermal highland circulation, and AABW may affect the global climate. And in our study recently, we found that AABW has some change. First, his temperature increased, and his velocity dropped. And this event happened. We call it blocking event. And to find out what happened, the purpose of our study is that to explain changes in the deep ocean are connected to sea level changes. And this is our hypothesis. Variability in abyssal circulation is linked to sea level anomaly. And this is our method. We use satellite altimetry data to see the sea surface level, and use the correlation analysis to see the relation between velocity and the sea level anomaly. Then we use LADCP to see the background velocity data. And in the right picture here, we can see this is the CTD here, and there's a yellow color device. This is the LADCP. So we can see it's connected to the CTD. Okay, so to see what's happened in the AABW, let's see how the AABW works in the normal conditions. In the left picture here, we can see the potential temperature in this area with the depth over 3,800 meters. In this green diamonds here, this is the place we put our device like LADCP. And this place is the Vena channel. And below the Vena channel, there's a large area. We call it entrance of Vena channel. We can see all of the waters here is really low temperature as how we introduce the AABW. The temperature here is lower than 2 degrees. And let's connect this area to the right picture. This picture shows the velocity of AABW. Let's see the velocity in the below area. This area is the entrance of Vena channel, and the velocity here is really low. We can see the colors here is purple or light gray. So the velocity is around 0 to 10 centimeters per second. And when when the currents here go to the Vena channel, we can see it already speed up a lot. So, and this area is the Vena channel. We can see this is like a tube. Transport this water from the Atlantic Ocean to the north. And AABW is formed in the Vena channels here. And let's see in the green diamonds I showed in the last picture. We do research here. We put our device like the green diamond and blue diamonds here. These two diamonds means the more current depth. And this picture in the top shows the topography of the vena channel. And we can see the velocity in the vena channels is really faster than the velocity outside the vena channels. And just like I said, the green diamond and the blue diamond are the same thing, but we put one of them into green to see the velocity change with time, like the picture in the top, in the bottom. We can see the y-axis is the time scale and the y-axis is the velocity. We can see the velocity in this region is regularly changed, but there's something weird. It's like if we put a blue bar here, we can see in the first few years, like here, from the 2004 to the 2005, most of the velocity can be higher than the blue bar. But when it comes to the 2006 and the 2005 here, most of the velocity can reach the blue bar and the velocity really drop a lot. And this is the anomaly I said. The A beta velocity drop. So next I will connect the variability in abyssal circulation is linked to the sea level anomaly. This picture shows the correlation between sea level anomaly and the bottom velocity. We can see this color bar means if there's a higher correlation, the color may be red. Means, the sea level anomaly is really connected to the velocity. And we can see in the entrance of vena channel, there's a strong correlation area here. And the velocity of current in the red square area is affected by the sea level anomaly. And the currents here may be transported to the vena channel. So it means the current transport from the red square area makes ABW velocity change. And this is the blocking event. We can see the velocity change with time in the different depth. And we put some time period with a gray area. We call it blocking events since the velocity here is really slow. The velocity here is lower than 10 centimeters per second here. And from the last 4 years, 2003 to 2007, there's a blocking event. And we mark some time to A, B, C, D, E to see how the sea level anomaly really affect the ABW velocity in data. First, let's see the A pictures. This shows the relation between sea level anomaly and ABW velocity. See the color bar first. We name the red area to a positive and the blue area with a negative. So we can see in the entrance of vena channel, there's a large blue area. It means there's a negative sea level anomaly. And let's see the ABW velocity, 20.4 centimeters per second, which is really small. So it means there's a blocking event here. And connect these two, we can say negative sea level anomaly make ABW become slower. And in the other hand, we can see there's the strong red area here in the entrance of vena channel. And there's the speed of 40.3 centimeters per second in the vena channel, which is really faster than the last one. So we can say positive sea level anomaly make the AABW faster. And the picture A and B is the thing I showed in the last two pictures. And the conclusion we got can apply to the C, D, E. If there's the blue area in the entrance of vena channel, the speed of ABW becomes slower. And there's something more interesting. It's like we can see the color bar here. We can see the sea level anomaly only range from minus 50 to 25, which is a really small scale. How could this small scale really affect the current velocity in such area? This must be connected to the previous picture. This picture shows the velocity of ABW. Let's see, in the entrance of vena channel, the velocity here is really slow. And we can connect this picture to the correlationship of velocity and sea level anomaly, we can't see any high correlation in the area outside the Vena channel. We can see there's any relation between Vena channels here. So we can get a conclusion that sea level anomaly only significantly affect the area with low velocity. And that's why in this area, the velocity here is really slow. So there's the high relation. But if we go to the Vena channel, the velocity here is really fast. So we can't see any correlation shift here. And I do some small animation to see how the sea level anomaly affect the ABW velocity. So in a normal condition, ABW transport from the entrance to the Vena channels. But if there's a negative sea level anomaly, means the low pressure gradients, there's a slow reverse direction velocity generated. And if you compare these two, ABW becomes slower. For the same meaning, positive sea level anomaly shows up, and these two will make ABW become faster. So this is the take-home message. Okay, see the red color here. If there's the red positive sea level anomaly, there's the high pressure gradient and make ABW become faster, like the conclusion we got. And apply to a negative sea level anomaly, make the ABW become slower. And this is our hypothesis. It proved it. And this is our reference. And thank you for listening.
I think your presentation was excellent, and it would be even better if there were more explanation for the image.
I think you did a great job. The presentation had a smart and logical flow, and it was simple and easier to understand.
Just one point. I think I'm not quite. Maybe it's my problem. I not quite understand about your some specific words and their relationship. But I think you did a great job about your conclusions. Yes. Okay. Thank you.